Hi dear students, welcome to today's online class. Today we discuss the third type of molecular spectroscopy used in organic chemistry, that is nuclear magnetic resonance spectroscopy. This is the most powerful spectroscopy technique for structural elucidation. As the name indicates, this spectroscopy is based on the magnetic property of certain nuclei. We will see various fundamental principles related to NMR. We'll make a quick recap because you have already learned all these things in detail in the 5th semester. What is the origin of NMR? You know that as electrons are spinning, nucleus is also spinning. You know, electron is negatively charged, it's a charged particle and it is spinning and it creates a magnetic field according to physics, and it behaves like a tiny bar magnet. Just like that, nucleus which is positively charged is also spinning. That means the nucleons are spinning and that creates a magnetic field, a magnetic moment. So spinning nucleus is also behaving like a tiny bar magnet. Right? So what? See, this is a positively charged nucleus and suppose it is spinning. Okay? Spinning. It will create a magnetic field. It will have a magnetic moment. Now, such a magnetic nuclei is kept in an applied magnetic field. We have an externally applied magnetic field. Okay. We are keeping an external magnetic field B0. What happens? This magnetic moment will take up different orientations, having sometimes 2 or 3, depends upon the spin quantum number, magnetic spin quantum number of this nucleus, that is represented as I. As just like, you know, electron has spin quantum number that is half, like the nucleus is also having the spin quantum number I value. So based on the value of I, there will be 2I plus 1 orientations for this magnetic moment when kept in an applied magnetic field. Suppose it is in 2 orientations, it will be like one is aligned with the field having lower energy and the other is the magnetic moment aligned against the applied field that is having higher energy. Right? So a magnetic nuclei, when kept in an applied magnetic field, it will have different orientations. So what does NMR involve? NMR spectroscopy involves the transition induced between this nuclear spin energy levels of certain nuclei. Not all nuclei are NMR active. Certain nuclei like nucleus of hydrogen H1, C13, F19, P31, phosphorus 31, etc. These isotopes of these elements, their nuclei are magnetic. We'll put more examples later. So, when such nuclei are kept in an applied magnetic field, we can induce transition from lower energy to higher energy. That means, normally, the nucleus will be having this, suppose it is having this kind of clockwise spinning, having lower energy. Okay. When we send radiation, electromagnetic radiation, and that is coming from radio frequency. See, for NMR, the EM radiation use these radio waves. So when a radio frequency wave is sent to such a nuclei, it will undergo transition from lower state to higher state. This is what is NMR. So what is NMR spectroscopy? It involves transition induced. Why we say induced? Because for this energy separation to take place, we have kept an applied magnetic field. Okay, there are two main differences between other spectroscopy techniques like IR and UV visible compared to NMR. One is that the interaction here is of magnetic type. We know in spectroscopy there is interaction between electromagnetic radiation and the molecule or matter, right? Which can be of two types, electrical interaction or magnetic interaction. In the UV visible and IR, it was electrical interaction, but here it is magnetic interaction between the radiation and the nuclei here, right? The second difference is that transition is induced, means we need an applied magnetic field for this to take place. Okay, we need to keep an applied external magnetic field for NMR, which is very costly, creating an electromagnet, a powerful electromagnet, and which require very low temperature. That's why NMR spectrometer is a very costly item. Okay, so this is NMR, the basic principle, the origin of NMR spectroscopy. Now, we move on to other points. What about the condition for NMR activity? Which all nuclei are NMR active? What is the condition? Condition for NMR activity, remember, this is a condition. I should be more than 0, where I is the nuclear spin quantum number. Spin quantum number of the nucleus, which should be more than 0. See, in a nucleus, there are protons, neutrons, which are all spinning. The resultant magnetic moment depends on the alignment of these nucleons, whether clockwise or anti-clockwise. However, for a nucleus to be NMR active, its I should be more than 0. That means it should have a resultant magnetic moment. Okay. So, how to predict whether a nucleus, whether a given nucleus is NMR active or not? It's not very easy, but there's a generalization. We can easily predict that based on this generalization. See, let me write number of proton, okay, number of proton and neutron in the nucleus of the given nuclei, and let's see how will be the value of I, and we'll put example. See, remember, for I to be more than 0, the selection rule for NMR activity, or the condition, necessary and sufficient condition for NMR activity is that I should be more than 0, or it should have a finite value, for which the condition is that number of proton or neutron or both should be odd. This is the point. When I will be more than 0, you can easily predict, for which the number of proton or neutron or both should be odd. At least one should be odd in this, that of number of proton and neutron. So let us take 3 cases. Okay. One is that both can be even, right? Like for example, if you take carbon 612 isotope, carbon 12 isotope, 6 proton, correct? That is even number. Number of neutron is 12 minus 6, that is 6, again even. In that case, I will be definitely 0. It will not be NMR active. So this is an example for a nucleus which is NMR inactive, because I is 0. So if both are even, it will be 0. The second possibility is that both are odd, right? Both are odd. Example, nitrogen 714. 7 proton, so odd number. 14 minus 7, 7 neutron, again odd number. Okay. In that case, definitely because both are odd, that means definitely it will have I more than 0, and the value will be integers, whole numbers like 1, 2, 3, etc. You get integral value for I in that case. Now the third case is either of these is odd, only one is odd. So it can be like odd even combination. One is odd, the other is even. The example here is H1. The nucleus of hydrogen atom. One proton, and what about number of neutron in hydrogen? The H1 isotope that is called protium doesn't have any neutron, you know that. So it is like proton is odd, neutron is 0, means we can take it as even. Another example is carbon 613. 6 proton, so proton number is even. What about neutron? 13 minus 6, that is 7, it is odd. So 1 is odd. In that case, definitely the condition is met, I will be more than 0, and it will be half integrals like 1 by 2, 3 by 2, etc. It goes like this. Okay, so these are the things. In both these cases, the nucleus will be NMR active. It will give NMR spectrum. So this is a condition for NMR activity. Now, next, in our syllabus, here in the 6th semester, we are dealing with only NMR spectroscopy applicable to hydrogen isotope, that is what we call H1 NMR. NMR is classified into various types based on the nuclei under consideration. It can be H1 NMR, that is also called proton NMR or PMR. Why? Because nucleus of hydrogen is just proton, there is no neutron. We can call nucleus of hydrogen as proton, so PMR. Another is C13 NMR, that is also briefly discussed in 5th semester, but not here. Here we have only proton NMR. So what about H1 NMR? What is the principle of H1 NMR? The nucleus under consideration here is H11. I value of proton is proton or hydrogen nucleus is simple, it is half. Henceforth we will call nucleus of hydrogen as proton only for our discussion. So I is equal to half, so it is NMR active. Can you say why this H1 NMR is most popular or it is most discussed? Because in organic compounds you can see plenty of hydrogen. The number of hydrogen will be maximum, right? So we make use of the hydrogen nucleus present in organic molecules for this NMR study. Now, see, I is equal to half for proton. Okay. Now, it is kept in an applied field. We are keeping proton in an applied magnetic field. What happens, as I said earlier, it will split into two states, two energy states, right? This is Mi equal plus half. That is the component of the different orientation of the magnetic moment, plus half, and the other is minus half. This can be represented as up spin, this can be represented as down spin, as I said earlier. So compared to the applied magnetic field, the magnetic moment of the spinning nucleus or the proton can be in the same direction, which is of lower energy, or it can be against the field having higher energy. Normally, the proton will be existing in this condition, that is applied, aligned with the field. Okay. See, what is written here is the degenerate state of these two levels in absence of field. Correct? That's by two lines. In presence of field, it will split into two with an energy gap here. Right? This energy gap is given by delta E is equal to Gn beta n B0. This comes from 5th semester. Energy of interaction due to the interaction between the applied magnetic field and the magnetic moment of this proton, there will be an energy gap. And this energy gap corresponds to the energy of radio waves. That's why we are using radio waves. So, if you are sending radio frequency wave to this nucleus, it will absorb energy and go to this state. So after absorption of energy, what will happen? This nucleus will go into this state. Now the spinning is just opposite, say it is anti-clockwise, so the spin direction is also opposite. So this is what is happening. In the low energy state, the proton goes into the high energy state. This is called spin flip. This is called spin flip, or this is spin transition. So energy is absorbed for this transition, and that will appear as a signal, NMR signal. So this energy equation, by Planck's theory, energy is h nu. So we can write h nu is equal to Gn beta n B0. What is Gn? This is called nuclear G factor. This is nuclear magneton, which are all constant values. B0 is the applied magnetic field. That's the variable here. So nu equal, we get Gn beta n B0 divided by h. H, you know, is Planck's constant. So from this you can see that nu is proportional to B0, right? When we change the strength of the applied magnetic field, frequency of the radio wave used for the transition also varies. It is directly proportional. If you plot a graph, you will get like this. If you are plotting a graph between B0 and energy or frequency, you can see it goes like this. When you increase the applied the strength, field strength, energy gap also increases. So frequency required also increases. Okay? Right. So this is the basic principle of proton NMR. Now, another important basic principle coming in this NMR is that what is known as diamagnetic shielding. See this equation nu equal Gn beta n B0 divided by h. This equation gives the frequency of the radio wave required for the transition of the nucleus. Now this equation is applicable for an isolated nucleus, but if you take a molecule, for example an organic molecule, CH3, CH2, CH2Cl, suppose chloropropane, one chloropropane. You can see there are two protons, two hydrogens here 2, here 3, correct? Now these protons are present in the molecule, and if all these protons are absorbing the same frequency, suppose all these protons are absorbing the same frequency of radio wave for transition, then you will be getting only one NMR signal for the whole molecule. Or if you take any molecules, you may get only one signal which is of little use. As a matter of fact, NMR of a molecule gives more than one signal. How does it happen? See, this equation is for an isolated nuclei, but the proton are present in the molecule, and that will have different frequency for transition. We will understand that now. See, it is based on what is called diamagnetic shielding, a very important concept coming here. See, you know, this is the nucleus, right, which is spinning and creating a magnetic field, you know. Now around the nucleus there are electrons, right? For every atom, you know, electron density is spherically arranged in the 3D space, but when you keep an atom in presence of an applied magnetic field, you know what happens? This electron density will confine to a plane, and this electron is electrons are revolving around the nucleus in a circular fashion, suppose like this. Okay, so these are the electrons around the nucleus. The point is, Around the nucleus there are electrons revolving. You know that electron is also magnetic because it's a charged particle. You know that an electron moving in a circular fashion, like it acts like a circular current loop, right? In physics you know that as a circular current loop will have a magnetic field, or this electron will create a magnetic field generally in this direction. It will be coming in this direction. These are the magnetic flux lines, okay, of the two poles. You know that these are the magnetic flux lines. So the point is, this secondary, the electrons revolving around the nucleus will generate a secondary field, right, which is generally opposite to the applied field. Now, when you take a molecule, for example, as I said earlier, CH3, CH2, or you take this simple example, chloroethane, you know that chlorine is electron withdrawing due to minus I effect. When it withdraw electron, electrons around these two hydrogen, okay, if I am writing it separate like this, H here and H here, electrons around these two protons will be much less than electrons around these three protons, because minus I effect will decrease the distance. The point is, electron density around different protons are different. So this secondary, this is called the secondary magnetic field. This field generated by the circulating electron is called secondary magnetic field, which is generally opposing the applied field. See, when you apply a magnetic field to this nucleus, which is spinning and creating a magnetic field, these circulating electrons are generating a secondary magnetic field which generally opposes the applied magnetic field. And this secondary field, magnetic field generated by the circulating electron will be different for different protons. That depends on the electron density around it. Okay, so that is given by so this induced secondary field is given by sigma B0, where sigma is the shielding constant, and so when you are applying B0, you have an induced field in opposite direction. So what will be the resultant? So the effective field felt by this nucleus will be less than the applied. Okay, you are applying this, but there is something opposite. So effective field felt by the nucleus will be B0 minus sigma B0. So that's equal to B0 into 1 minus sigma. So the point is that due to this secondary field generated by the circulating electron, nucleus will be getting only a reduced field compared to the field strength changes, frequency also changes, correct? Since the electron density is different around each hydrogen here, they will have different field, effective field. Now it is to be written effective field, okay, that will be varying, so frequency will be varying. So you get different signals at different frequency. That is how we are getting different NMR signals for the molecule, and that gives a lot of information. When you are getting different signals, what you understand? The molecule contains different types of, chemically different types of protons. This is called diamagnetic shielding. Why? Because you are applying this external magnetic field, and this secondary magnetic field due to the circulating electron is opposing it. So it's shielding the applied field. That's why shielding. And diamagnetic, you know, when they are in the opposite direction, we call dia. See, when there are two electrons which are parallel, what you call? Same spin. In the same spin we call it paramagnetic, correct? And when the spins are paired opposite, it is called diamagnetic. So this is called diamagnetic shielding due to the secondary electrons. Now, based on this understanding, we can make an application. I mean, we can go to some examples of how to predict the number of NMR signals in a molecule. It's a very interesting application of NMR. Predicting number of NMR signals. Okay, we can take a few examples. and number of NMR signals of various molecules. See, it depends on the chemical equivalence of the protons, chemical environment of the protons. Let me write the first example. CH3, ethane. It's very easy. I am writing another example. See, for example, benzene. If you take another example is CH3OCH3, that is dimethyl ether. See, you can classify these protons like this. If these three protons are marked A, what about this one? Same, right? We call they are chemical equivalent. That means these will give only one signal. What about benzene? You know, benzene has got all carbon having one hydrogen, right? All hydrogens are in the same chemical environment, no difference. So that will also give one signal. What about this one? If this is A, this is also A, one signal. Let me take another example. See, CH3OH. What about this one? Methanol. If these three protons are marked as A, what about this one? Connected to oxygen. Correct? This is connected to carbon. Different chemical environment. So this is to be labeled as B. Two different types of protons. You will get two signals. Okay. Look at another example. Another interesting example. See. What about this molecule? What is this molecule? This is 1,4-dimethyl benzene or paraxylene. Correct? If you classify the protons, this is A, then this is also A. Now you know that benzene has got in the ring there are 4 hydrogens here, and these are in different chemical environment. If this is B, these are all B. So there are two different sets of protons, so there are two signals. Finally, if you take another example, CH3, CH2OH. What about this one? You can label them. If this is A, this is in different bonding condition, right? The chemical environment is different, the connectivity is different, and this is C. 3 signals you will get. See, look at another example. Okay. Here, suppose it is N here. What is this molecule? This is pyridine, correct? And if you look at various ring protons, how can you classify them? See, when nitrogen comes here, it is highly electronegative. It will change the electron density around these protons. If this is A, this is also A, correct? If this is B, this is also B, and this is C, correct? So there will be 3 signals. Interesting. I have 2 questions to you related to this one. Number 1, you should note that question. Number 1, write 2 examples each for molecules giving 2 NMR signals as well as 3 NMR signals. I am giving number of signals has to be 2 and has to be 3. You write 2 examples each for these 2 cases apart from what we have written. Not these examples, you write new examples. And second question is, so that is question number 1. Second question is a very interesting question. See, a molecule is having the formula C5H12, right? This is the molecular formula of a molecule, of a compound. And the information is that this is giving only 1 NMR signal. This compound gives only 1 NMR signal. Predict the structure. See, only this information can lead you to the structure of this molecule. That's why I said NMR is most powerful technique for structural elucidation. So what is the structure of a compound having this molecular formula C5H12 which gives only 1 NMR signal? Okay, see you in the next class. Thank you.